Hello, so today we are going to continue on weekly contest 326, which is this week's contest. So we get an array of numbers of positive integers, and we want to return the number of distinct prime factors of the product of the elements of the array, right? So, for example, with this array, the product of all elements is 2 by 4 by 3 multiplied by 3 multiplied by 7, 10, 6. We get this number, and the prime factorization of that number is this. And so you can see here we have 4 prime factors, so we return 4. Okay, and then just two things mentioned here. The first one is that a number greater than 1 is called prime if it's divisible by only 1 and the number itself. So for example, 7 is only divisible by 1 and 7. And then an integer value 1 is a factor of another one if value 2 divided by val1 is an integer. So basically it's saying that val1 is a factor of val2 if val2 is divisible by val1, right? So that's the idea. Okay, so now this is the problem. In terms of constraint here, we have up to 10 to the power of 4 numbers. So definitely we can do an O(n) squared solution. But we also have a constraint on the value of the numbers themselves. They can be up to 1000, right? So how do we solve this? Okay, so how do we solve this? So one thing the problem says is that the numbers in the array can be up to 1000, between 1000 and 2, right? So what we can do is pre-generate, just to make it easier. The number of elements can be up to 10 to the power of 4. So the first thing is to make it easier for us to find if a number is prime or not. We can just pre-generate all the prime numbers up to 1000 because that's the max, right? So we can just have a prime Boolean array, right, that says whether a number is prime or not, and it says it for all the numbers up to 1000. And that you can do it in the main way that's usually done is using this thing called sieve of I think Eratosthenes. It's a little bit hard to pronounce, but it's sieve of Eratosthenes. Yeah, you can Google it essentially, but the main idea of that we will explain it in a moment. But let's first give the general idea. So what will it be? So for example, for 0, the index 0, is 0 a prime or not? Right? 0 is not a prime. Because we will consider 0 first and 1 not a prime, and then we'll start initially with all the other ones true. And then what we'll do is we will go through the numbers, right, from 2, so this would be 1, 2, from 2 up to 10,000, up to 1000. And so we'll start from 2, and what we will do, we know that 2 is prime, right? And so initially it will be set to true, so because 2 is prime. But what we'll do is we will mark all the multiples of 2 as not primes. Why? Because 4 is not prime because it's divisible by 2. 8 not prime, it's divisible by 2, right? So all the multiples of 2 are by definition not prime because they are divisible by 2. So we'll go through all of them and just mark them as not prime. So this would be false. And then 8 down the road will be false as well, all the way until we reach the limit. Okay, and we can do that with just a for loop with the increment each time being 2. And then we'll move on to 3. If 3 is still marked as prime in the array, then that means it's prime. And so what we do is we go and mark all the multiples of 3 as not prime because they are divisible by 3. So I'll go mark 9, mark, I don't know, 3 by 5, maybe 15, right, as not prime. And so we'll mark all the multiples of 3 as not prime in our array. And then we'll move to the next number, 4. But we'll find that 4 is not a prime, so we skip it. We don't need to do anything. And then we go to 5.
5, we haven't marked it yet as not prime, right? And so that means it's prime. So basically, if we reach a number and we haven't set it to not prime yet, that means it is a prime because we haven't found anything before that divides it, right? So that's the main idea of this sieve of Eratosthenes here. And by the end, once we reach 1000, we'll have this table filled with the appropriate value for each number, whether it's prime or not. Okay, so that would be the step 1 using this algorithm here. So once we have our primes, right, in this array, we can extract them in sort of a list, right? And so, for example, it would be 2, 3, 5, 7. Those values will be set to true in our primes Boolean array. And then you could go all the way up to 31, I think is the last one, or something. Maybe there are more, but 31 is definitely there. Okay, so now we want to find, the original problem asks us to find the number of distinct prime factors. That's what we are looking for. Okay, and so in the array that we have as an example, 2, 4, 3, 7, 10, 6, right? So what we will get is the product, which is the multiplication of all of them, right? So for something to be a prime factor of prod, it definitely can be like 2 multiplied by 4, 8, because it's not a prime, because by definition it's the multiple of 2 of them. It can be anything, so it has to be either one of the elements in the array or something that divides one of the elements in the array. Right? Because if we multiply maybe 2 together or 3 together, we'll never get a prime number, because by definition we are multiplying multiple numbers, so it's divisible by all these numbers, so it's not a prime. And so it's either one of the numbers or a prime that divides it. Why did I say prime that divides it? Because product is the product of all of these, right? So for something to divide this, it has to divide one of these numbers, right? So that's the main idea. So what we can do in this case is just go through the numbers in the array. So we can just go through the numbers in the array in this case. And then for each one, what we are looking for is we are looking for a prime that divides this x. Because if we find it, that means it will divide the product. And if it's a prime, that's something we want to count, right? And so we'll have because a number may divide maybe multiple of the numbers in the array, we want to make this a set so that we don't overcount, right? And so we can just go through the primes, because we already pre-calculated them here, right? And check if any of them divide x, because then that means it's a prime factor of prod, right? And so if any of them divide x, so x is divisible by p, then we want to add it to our factors of the product, right? So factors of the product. Okay. We can do slight optimization here, which is if we reach a prime that is bigger than x, let's say maybe, I don't know, we are at 7, a prime 7, and we are looking at 2. There is no need to look at that, right? And no need to look beyond, because it will never divide x because it's bigger than it, right? So what we can do here is if we ever get a p-value that is bigger than x, we can just exit, at least for this x value, and go to the next number, right? And then at the end, we will have all the numbers. Either the number itself is prime, and we will get it from this because a number divides itself, or all those that divide each number of the array, and we'll count all of them as factors because they are all prime factors of the product, and then we will just return the length at the end, because we know they are distinct because we are adding them to the set. So at the end, we can just return the length of factors. Okay. So 2 ideas here. One is the way we compute the primes here using the sieve of Eratosthenes. The second idea is the fact that for a prime factor to be a prime factor of product, it has to be either one of the numbers or a number that divides, or a prime that divides one of the numbers. And that's how we are handling that here. Yeah, so that's pretty much the main idea. So let's implement it and make sure it passes. Okay, so let's implement the solution we just saw in the overview. So we said we need to define the prime factors. We need to find all the numbers, whether they are primed or not. So first we will suppose that they are prime until we check and we determine that they are not. And so we'll do that for all the numbers up to 1,000 because that's the limit for the numbers. So in Python, to get to 1,000, we need to do 1,000 plus 1 here. Then we will mark prime 0 and prime 1 as false initially. So 1 as false each. And now we'll just do our sieve of Eratosthenes. Sorry, it's hard to pronounce. So it would be, we'll start from 2 because we already filled up to 1. And then we are going to do in range of 1001 again, because that's what we want to fill here. And then we'll check if it is a prime. Then we want to mark all the multiples of x as not prime because they are divisible by x. And so to do that, we'll just do I as all the multiples of x. How do we do that? We start from x by x because this is multiple of x. And we need to end at this limit, right? That's the last one we want. And each time we would want to increase by x because that's how much we want the multiples we want. We want all the multiples of 2, so each time we add 2. We want all multiples of 3, so each time we add 3, right? And so here what we'll do is we'll say now this is not a prime because it's divisible by a prime, which is x. So we'll say I is equal to false. Okay, so now that we have the value whether each number is prime or not, we can collect those values in a prime array. And so we'll say for x in range of 1001, if it's a prime according to this Boolean array, then we want to add it to the list of our primes. Okay. And now we'll do the core of the algorithm for to go through all the numbers. And we go through all the primes for each number and we check if any of it divide that number. That means it is divisible by it. So this is a prime factor for the product. And so we can add it to our factors. We add the prime, not the x value, of course, because the factors here are the prime factors of product, right? And if this prime is bigger than x, that means because this is in increasing order, so as we go we'll only get bigger values. And also if a number is bigger than x, it won't divide it. So, and as we progress to primes, we'll only get bigger values, so it will only be values that don't divide x. So there is no need to continue, so we can just break here. And then at the end, once we have all the factors, we can just return the length of the factors. And that should be it. So let's run this. Looks good there. Let's submit. And it passed it. Yeah, so that's pretty much it for this problem. Now, in terms of time, we are doing this nested loop here that you could say is roughly O of maybe to the power of 2. If we really are generous in terms of the limit. Yeah, I bet this is a lot smaller, but let's just for one now say this. And this here is O of. So in any case, both are constant because it's a constant value. And this is O of n. The number of prime up to 1001, I think it's constant as well. It may be like 20 or 30, something like that. So we can say this is roughly constant. And so overall it's O of n here. And of course, like this constant can be pretty big, up to, it's pretty big, up to 10 to the power of 3, 6. But if n can be up to 10 to the power of 4. So roughly it's O of n-ish with some significant constant factors. So that's in terms of time. Now in terms of space, we are using this extra space here for is prime. So this one is O of 1000 roughly. And then we are using this prime, which also is the number of primes, 20 or 30. It won't exceed definitely 1000. And these factors, same thing, they won't exceed the number of elements that the 1000 here. Yeah, so roughly the factors maybe can be O of n multiplied by this. So we can say roughly constant O of n space as well. Yeah, so that's just my guess would be here for the time and the space. Yeah, so yeah, that's pretty much it for this problem. Please like and subscribe, and see you on the next one. Bye.